Thanks the organizers and the sponsors for making this workshop happen. So if you look in the program, this talk is built as a special session, no? And it's not a normal presentation because I will not present any recent paper, I will not present any results, but I have this new hobby, which I think you should all know about. And yeah, I've learned a system so that you don't have to, and I will just report on my results. So consider me a tourist guide, and I will guide you through, you know, a new country of ideas. Okay, right. So it used to be that humanity paid people to do menial labor, and now this is completely, utterly outclassed by machines. No, for example, for digging holes. All right, and it used to be that people then were used for, you know, repetitive mental labor. For example, my grandmother, she had an encyclopedia in her home, and if you opened it and looked up the entry for computer, it says a person who computes. Yeah, like these people. And they are no longer, they're completely outclassed by machines. No? And so it goes, but of course it doesn't apply to us, no? Because we are pondering, you know, the deep questions of, you know, foundations of quantum physics, and, you know, the machine can't do that. Yeah, maybe, right? But of course, we can cope. You know, there's apparently that's how the young people talk on the internet. They say there's cope. Namely, we can say, yeah, there's nothing to worry about. For example, these machines are too unreliable to do mathematics. They hallucinate. No, they can't prove theorems. And so we are safe, right? I mean, and yeah, nervous laughter. Okay. So I want to tell you about, not actually about LLMs, even though that was kind of my introduction, but I want to tell you about a complementary technology that is also now getting ready for prime time, and that could, you know, help LLMs to bridge their credibility gap. And so there's this technology is you know, maybe you've heard about it. It's called formal proof checkers. Yeah, formal proof. So proof can be modified to be even more formal. That's what it's going to be about. So it's an old idea in mathematical logic to have a computer program that would automatically verify whether a mathematical argument is rigorously true or not. And even though it's an old idea, it has only recently, in the past maybe 5-6 years, really hit escape velocity. I think, you know, it's much more usable today than it was a few years ago. So here's some statistics to back it up. So like, yeah, MathLib is one of these systems called Lean, and MathLib is the biggest, you know, math library. And you can see here the contribution graphs, and there's like lines of codes, the y-axis, and it has surpassed 2 million lines of codes when I took the picture, but now it's at 2.5 million lines of codes. So there's a lot of activity going on. And yeah, well-known mathematicians, yeah, Terence Tao, for example, is writing a new edition of his Analysis 1 textbook together with the Lean implementation of all the proofs. Yeah, so this is being taken very serious by very serious people. So could this be the future of math research, where we've created our super machine that is completely, where a human stands no chance against it, by combining these two technologies, by having the creativity of LLMs, and don't really mind their unreliability because we can couple them with these formalized proof checkers, which are extremely pedantic, but in a team they could really beat us. So it could be that this is the future of math research. I don't know whether it will be. Maybe also the LLM sites become so good that they don't need these, you know, formal checker crutches anymore. I don't know that, but I think it's rather likely than not that these things will become much more important in the future. And so I decided to spend some time learning it, so that when the artificial intelligence fires all of you, it will employ me for another month before it fires me. And I hope you know, will then welcome me back into the ranks of. All right, okay, so good. So first, if I tell people about it, I have the feeling, the problem that everybody has used computers for math in the past, and people snap to assumptions. What happens when you combine a computer with mathematics? So let me try to put it on the map a bit. You know, what are these systems about? So let's say you want to, for example, treat a system from classical mechanics or something. No, so then you can use the computer for various tasks. For example, if you want to integrate a vector field to get a numerical trajectory, use Julia. No, it will give you like some time evolution. Yeah, or maybe you have one of these rare systems that are actually exactly integrable. Then you use Mathematica, and it might give you an integral. Yeah, or maybe you want to say stuff like this. You want to show that every Lipschitz continuous vector field admits an integral curve. the don't laugh. It's the theorem of Picard-Lindelöf that I at least mentioned in my Mechanics 1 class that tells you that mechanics is mathematically well-defined. So yeah, these Hamiltonian equations actually have solutions. And that's a typical example of pen and paper mathematics. No, you would not use a computer system. You would not let it get near a computer system before. No, and this is stuff we cannot do. In particular, what we cannot handle are these systems. What they can handle, they can handle like for all quantifiers. They can talk about the infinite. They can do functional analysis, stuff like this, right? So it's real, epsilon delta kind of rigorous pen and paper math, the thing that goes between the begin proof and end proof environment in your papers. All right. Okay, so there's one difference, though, where my analogy breaks a bit down. So let me warn you. So Julia computes this integral curve for you. No, you don't have to do it. Julia does it for you. And Mathematica integrates, so you don't have to. But Lean, the system, they don't find the proofs for you. No, they check whether a proof that you supplied is actually rigorous. And so it's a kind of like an adversarial game. They have very high, very pedantic standards, and if you like formalize a program statement, then it will not fill in the proof, but it will ask you, so why do you think it's true? And then you go like step by step, try to convince it, and most of the time the system will say, I don't get it, until finally, eventually it will get it, and then it's, and once it's accepted by the system, then you can know rigorously it is actually true, Yeah. Another word for these systems is they're called proof assistants. But if you learn them in the first month, you will think of them as proof opponents pretty quickly, because they kind of have a tendency of working against you. All right, okay, so good. So now you know a bit what, which universe I'm living in. And so I can now actually give the outline of my talk. So I will now for, 50 minutes or so tell you a bit about the logical model of Lean. So the way I got into it, now I'm justifying it with LLMs, but actually the reason was that there's this week between Christmas and New Year, when all the administrators are at home and don't write your emails and the students don't come, and you can learn something new. And so like 2 years ago in the Christmas break, I wanted to learn some mathematical logic because I'm now old enough that I don't need to write PLs anymore or something. These systems are, it pays to know some mathematical logic. So I'll tell you a little bit about the mathematical logic model of these systems, how they work. I think it's very interesting conceptually. And then I thought about what to do. I could do some live coding thing, but maybe it's too boring. I don't have time. So I've just compiled a long list of little FAQs and stories about, that I picked up in the past year visiting these ecosystems. And I can tell you a few until you want to go to the coffee break, and then I stop. All right, good. So first, let's talk like a very brief history of mathematical truth. Now, of course, I'm not a mathematician, and I'm not a logician, and I'm not a history of logics person, so I know nothing about this. I'm really like a dilettante. So if there is an actual historian of mathematical logic in the audience, maybe you want to get your coffee now in order not to get a heart attack. I think everything I say is directionally correct, but all the details might be a little bit iffy. Okay, good. So yeah, math and physics. So, how did it happen that we, got divorced? No, we used to be one family. So there's Leibniz and Newton. Were they mathematicians or physicists? We can't really say. No, when they developed calculus, for example, they didn't have like a logical foundation for that. There was no axiomatic basis for a long time. But still, the stuff they came up with actually works. And so why is that? And I think it's because at the point the math was tethered to physics. So they limited their statements to systems that have a model in physical reality. So even though they didn't have a rigorous logical foundation, it actually, reality guided them to do sensible things. And there's this famous essay, which you may or may not know, by Wigner. It's called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And he wonders why it is that we are so lucky that our universe, or many aspects of our universe, can be described by mathematical formulas, or why like easy formulas often turn out to be true. There's no guarantee for that at all. And I think I want to read it the other way around. So if you don't know mathematical logic, but you have a good physical intuition, that turns you into a surprisingly decent mathematician. No? And so this is, why math worked maybe in prior centuries. But around 1900, this changed, and mathematicians wanted to start making statements about objects that are no longer tethered to physics at all. Yeah, here's a famous example. I guess many of you know it. Here's a famous example that everybody with a math education will tell you is true. Yeah, so you can do the following: you can take a solid ball in 3 dimensions and you can break it up into sub pieces, and you can move them around and rotate them in such a way that you end up with 2 solid balls of the same radius. Yeah, it's called the Banach-Tarski paradox. It's provably correct. It's in Lean in MathLab. You can check it out if you don't believe me. But of course, whatever brings mathematicians to agree that this is true is not physical intuition. No, obviously, these subsets can't model anything you can do to an actual ball. No, this is completely impossible. Yeah, it relies on the existence of unmeasurable sets, yeah, which nobody can construct. Yeah, but if you assume they exist, then this is true. Okay, and so so today it's no longer tethered, mathematical truth to physical reality. And so what happened in the middle around 1900? And what happened is that math came up. The community of mathematicians, they came up with an accepted model for how to decide whether something should be admitted as mathematical truth. And one thing I learned is that this wasn't smooth sailing at all. There were fights, and friends became enemies, and there's a very high rate of suicide among the early logicians, and people literally died in the asylum. And what were they fighting about? Okay, so they were fighting about how to set up a system for deciding what is true. And in the end, of course, we probably know that from your math education, like formally, like a mathematical proof is a sequence of deductions operating on axioms. No? So you have a small number of axioms, and then you have, which is more important and less talked about, so let me talk about this now, you have a mechanical method so some of the state of your knowledge is modeled as a list of statements that you have proven, and then you take a few of them and you can combine them to derive new true results. No, that's a deduction. So what are deduction rules that are valid in logic? Let me give you a few examples, and if you fall asleep, don't fall asleep just now, because people fought about over these, okay, it can't be that boring. Here's one, modus ponens. No, if in a list of proven statements, there's a statement P and another statement that says P implies Q, then you can conclude, in fact, that Q is also true, and you can put Q onto your list of proven statements. There's bewildered smiles in the audience. They are not so obvious. We'll get to some problem in a second. Yeah, another one, conjunction introduction. If you have P and Q, then you can also add P and Q into your list of true statements. So these are deductive rules. And the big fight brought out is what kind of deductions are legal. And yeah, there's 2 people here. I don't think anybody will recognize them, no? Sorry? Russell. Yeah, Russell will also appear, but it's neither of them. Very good, though. Well, yeah. So that is Cantor, and that is Kronecker. Kronecker used to be the teacher of Cantor, and then they fell out over these things. And Kronecker, this guy, is going to be the conservative guy. He will appear on my slides more often. And so, all right, let me try to explain you about this fight. By the way, if you want to learn about this fight, and you're like me, starting very late in life, learning about mathematical logic, then I recommend you get a copy of this logic comics from the library, where this period is presented in a very digestible form, and you set Russell, and in fact the main character is Russell. So there's Russell here who tampered with infinity, and that's the statue of Gauss going after him. That was just a side remark. Yeah, but let me explain, what this fight was about. Okay, so, so before we even get to logic, maybe we have to agree on a philosophy of mathematics. Shall we do this real quick? Okay, let's adopt the Platonic model of mathematical truth, where we believe, and if you don't believe it, then the rest of the talk is not for you, that every mathematical statement has an intrinsic truth value. Yeah, so every Turing machine either holds or doesn't hold. Yeah, you have to agree that this is true in some Platonic sense. Okay, agreed? Well, okay, good enough for now. All right, and then we come, then let me introduce classical logic. So classical logic is what math today operates on. And it says that, okay, so what deductions are legal? Well, deductions need to be truth preserving. If you have a list of true statements and you want to add a new one, you know the rule for doing that better, you know, make sure that you only add true statements to the list. And classical logic says that's all. You know, if you have any move that you can argue preserves truth, then it's a valid deduction rule. Seems reasonable, no? There's a problem, though. It may give rise to non-constructive existence claims. All right, maybe you've been exposed to it. Here's a very famous one. Let me give you a famous one. It comes via the law of the excluded middle. So the law of the excluded middle says is the following reason in principle. It says that if P is any statement, then the following is true: P or not P. That sounds okay, no? P or not P. Aha, yeah, you're nodding along, but this leads to problems. For example, here's an argument. Let me give you a statement, and then I will prove it using the law of the excluded middle, and then you will see that it's a bit strange what comes out of it. Yeah. So here's the statement. It says there exist two irrational numbers a and b, such that a to the b is rational. That's a claim. It may be true or false. Maybe you don't know, but let me prove to you that it's actually true. Here's a proof. And it has two arms, you know, two cases. First, I assume that root 2 to the root 2 is rational. Well, but if root 2 to the root 2 is rational, I'm done, because we know since the ancient Greek that root 2 is irrational. So I got an irrational to the irrational, which is rational, so we are done. Okay, or using the law of the excluded middle, let's assume root 2 to the root 2 is irrational. Well, then I take a to be root 2 to the root 2 and b root 2, and I compute a to the b is square root of 2 squared, which is 2, which is rational. So in either case, I'm done. Okay, so it's a cute mathematical proof. But are you now convinced? Because we've now, Miguel is convinced. But you know, but I've now asserted the existence of a pair A and B with a certain property without giving you any example. Now, we don't know which of the two, I mean, by we, like we now quickly in the audience, don't look it up because it's of course known, which of the ones actually realized. But if you just have this argument, you wouldn't know. And people like Kronecker, they would reject this. They would say, that is not mathematics, this is theology. Because an actual quote, not by him, but from the time, because you know, you believe in the existence of an object without having an example of that object. And so there was a counter movement that would reject any kind of logical deduction that would give rise to these statements that are not backed up by a construction. They are called traditionally intuitionists, which is a very bad name. And today it's intuitionist sounds like it's like hippies who would say anything goes, but they were much more conservative than classical mathematicians in the set of rules they allow for. So it's not a good name. I will call them constructivists, which is also, I guess it's not exactly the same, but it's close enough for our resolution. Okay, so then, you know, what did the constructivist, what was their counter offer? What should be a legal rule for derivation, for deduction? And there's one, it's called the Brouwer-Heiting-Kolmogorov rules that preserve both truth and constructibility. Yeah, so it's fewer moves are now legal, and we have a higher standard as to what can constitute a mathematical proof. And I will give you a few bullet points so that you get a feeling for how they tell you you can manipulate your list of truths so that you preserve also constructibility. The first one is super boring, just as a warm-up. So let's say you want to deduce a conjunction P and Q, then you must supply a proof of P and a proof of Q. Okay, so if you want to say two things are right and two things are constructible, you gotta have to prove that they're right and constructible. Now it gets more interesting. To deduce a disjunction P or Q, you must supply a proof of P or a proof of Q. And this we haven't done, no? We have used a disjunction in our reasoning, like the first and the second bullet point, but we have not given a proof for either. Okay, so they would have rejected our argument. Yeah, so the law of the excluded middle is not generally valid. And now it gets very interesting. So if you fell asleep, you have to wake up now, because it's like one of the core messages here. To deduce an implication P implies Q, you must supply an algorithm for turning a proof of Q into a proof of P. Interesting. No, it's in the 1920s, you know, before computers were widely available. But this way of thinking is going to be very interesting. And similarly, to deduce a universal statement for all x p of x, you must apply an algorithm that takes x as an argument and computes a proof of px. And then there's many more rules for the different logical constructives. I don't want to bore you, but sorry. Oh, yeah, that's right. I've got my directions wrong. Thank you. Okay, yep, that's right. Okay, but like this is one. Yeah. Now that Miguel complains about my slides, let me tell you, on the airplane he sat next to me and said there's only one thing he learned after turning 40, namely, in your case, was harmonics, no? How to appreciate chords and stuff like this. And here's one thing I learned after turning 40, and it's a new way of thinking about a theorem. Yeah, what is a mathematical theorem? And from this point of view, it's a very nice point of view. It says a theorem is an algorithm that turns a proof of its assumptions into a proof of its conclusion. Okay, keep that in mind. That will become very important. Okay, I will, to see how this feels, let's look at induction, mathematical induction. I will first remind you, like from your elementary school, how mathematical induction is handled in classical logic, and then we do the constructivist version. So here's a classical version. So you consider a predicate, P n on n. A predicate, to remind everybody, thing work? Okay. A predicate is a, like for every natural number, you have a claim, like, I don't know, yeah, some theorem, some statement that depends on n. Okay, you want to prove that it holds. And then if you have, so induction says that if you have a proof of p at 0, the base case, and you have a proof, the induction case, that if p of n is true, then p of n plus 1 is also true, then you can conclude that p actually holds for all n. Yeah, it's an axiom in piano arithmetic, right? And let's reformulate it from the constructivist point of view. Yeah. So in constructivism, like, okay, let's say you have a proof HB of the base case. That's still the same thing. But now look at this. That's an implication. So that's an algorithm in their point of view. So you have a function HI that turns any proof of Pn into a proof of Pn plus 1. Now I got it right, no? And if you have that, then you don't need an axiom for concluding that that P holds for every n. You can compute a proof for Pn for every n, namely by recursion. So here's a piece of pseudocode that is what these lean systems literally implement when they do recursion. So let's say you got a function, like, so a theorem, because a theorem is a function, and it takes n as an argument, and then if n is 0, it returns the proof of the base case, else it returns, well, it calls itself recursively with n decremented, and then it gets a proof of Pn minus 1, which it plugs into the function hi, which gives you a proof of Pn. Yeah, and by recursion, it will call itself, or repeatedly until it reaches the base case. Then it will return, and the recursion will unravel, and that's how it works. So you don't need so there is no difference between recursion and induction is not an axiom. Okay, you can see it's a fruitful way maybe of thinking about mathematics. Okay, so now let's go back to these computer systems, Lean. So they use this point of view. So Lean, what Lean is, it's a programming language that happens to be well suited for implementing functions on mathematical statements. You can also write arbitrary your computer code with it if you like functional programming. I don't know. Yeah, okay. So this Kronecker says, yeah, so his old ideas that kind of like died, he lost the fight against classical mathematics, but he's very happy that these ideas live on. However, now comes part 2 of the logic. There are demerits to this approach. So let's say there's a statement proved by induction, and you want to know, does it hold for 10 to the 9? That gets pretty expensive, because now you have to call yourself recursively, a billion times. Maybe you have a stack overflow error or something, so that you don't want to do. There's another demerit, namely, there is a lot of, let's say, axioms, for example, that are not constructive, that are used today in mathematics, like, I don't know, the axiom of choice, which gives you the existence of non-measurable sets, which powers the Banach-Tarski paradox. Now, Kronecker would, of course, say that's good that you can't say it because he doesn't believe it's true. But modern math has been using it since half a century, and there was no big problem with it. So it would be very bad if a system couldn't do it. So we need to add a little twist to this computational logic to make it a bit, to address these two problems. Okay, and now that's the second idea from logic. Oh yeah, Kronecker is very unhappy. Boo. Okay, shut up. All right, and this is solved using something called type theory, and this is now a bit out there. So this is very okay. That's the second thing I learned after turning 40. Okay, so what's a type? Okay, so in some languages, like variables are typed. So if you want to have like an integer, you write int x for the variable, or if you have a floating point number, you write float x for the variable. Of course, the young people, they grew up on Python or whatever and get all cuddled, and but like back when we were coding in the trenches, we had to type our variables. And why did they do it? For its various benefits. So one, back in the day, RAM was very expensive. So the type told the compiler how much space to allocate. An integer takes less space than a floating point number or something. But there's a second benefit, namely you can do some kind of static type checking. So the compiler can catch some mistakes if the types of things don't match. Yeah, here's a piece of C code I wrote. It says int x. X is a variable, it should be an integer, and then the right-hand side is a floating point number. And then when I compile it before I run it, it's not Python, it says, warning, there is, some iffy thing going on. Okay? So that's all right. That's type theory. And now, so okay, that's like a type system. And then I as a newcomer to the field, I read the term type theory, and that sounds like a bad joke. What can you say about this? Float is bigger than int. That's not a theory. That's the triviality. Yeah. And okay, now I do a little one slide that serves no purpose, but I want to show you something cool. It's kind of like a detour. Hold that thought. Yeah. So in computing there is this concept called universality. So it means that many systems are universal as computers. Maybe in a serious way. For example, you can you can model computations using Turing machines, or if you are in quantum information, maybe you like gates and circuits better. And I gave this this talk at a conference of Robert Rausendorf, so I had to mention cluster states, also universal model. But then there are also systems that are universal in an unserious way. It's a kind of hobby in computer science. There's like websites called accidentally Turing complete that list all of the systems that really shouldn't be computers but actually are, like HTML, or Minecraft apparently, or PDFs. And this is what I want to show you. So, in case you don't know it, so here's it's on the wrong screen now. I have to get it on the main screen. No. Oh, I wanted to make a quick interjection, but now I'm too stupid to get it to the main screen. Is it? There it is. Okay. Okay, now I have to hit it. Okay, so there's a PDF. So PDF is a language for describing pages, but it's also delayed. Oh, that's going to be very difficult. I have to hit this. Yeah. Okay, but apparently PDF is also Turing complete. So any computer code you can write at all, you can write in a PDF. And so people brought a Doom to a PDF. There's a Doom PDF. And this is a PDF, yeah. You can post it on the archive. All right, good. And so I don't, now I have to go back to, now Doom is running on my computer. All right, now, okay, so maybe I can continue with my talk. So now, like int and float is too simple of a type theory, but I believe maybe there's horrible type theories that are so complicated that you can put all of mathematics into your type checker of a compiler. And then people like me would go, how do I use this computer? No, my joke. Okay, the punchline. Okay, play from current slide. Okay, all right. Now I'm back. Good. And now, like people like me go, Doom in a PDF, that's hilarious. Next, you'll cram all of mathematics into your compiler's type checker. Am I right? And then come these type theoreticians and say, yes, this, but unironically. So now let me explain what this is all about. All right. Okay, so associated with, what does the system do? So associated with any statement, they create a new type. It's a type of all its proofs. Okay, and so once you have that, you can revisit the example we had before. So the term HB has type proof of the base case, and the function HI has type function that turns proofs of Pn into proof of Pn plus 1. And if you have it, then you can see that this little function we have is well typed, meaning it claims to return a proof of Pn, and it actually does. Yeah, you can do it, verify it using static analysis. If n is 0, then it returns HB, which has type proof of P0, and HI needs an argument of type Pn and returns one of Pn plus 1, and it gets one of type 1 lower and returns one of type higher. Everything checks out. So the type checker will say, yes, I can compile that. Yeah, and so because this thing is well typed, we know it will return a term of type proof of Pn if we run it on n. Okay, but now that we know it will give us a proof, we don't actually need to run it anymore, no? Because in math, we just want to know is the theorem true or not. And so this has a name, this realization. It's called the Howard-Curry correspondence in computer science. And it goes like this. Let me summarize again. So to prove a theorem, you have to construct a well-typed function. And proof verification is static type analysis, where you don't actually run it, but just check, would it give me a proof if I would run it? Yeah, and then another, so you don't have to actually run the recursion anymore, so we got rid of the runtime problem. Another thing we have now, we can now handle axioms, because if we want to put in an axiom like the axiom of choice, we just tell the type checker, you know, whenever you see this term called axiom of choice, accept it as well typed, but don't ask any questions. And then the type checker can handle it. You couldn't run it, but we don't necessarily need to run it anymore. We just, you know, need to run the type checking stage. So the ironic end state is now that we have millions of lines of codes in this MathLib repository that are so rigorously type checked that we don't need to actually run it. So it's probably the largest computer code written in human history with the intention to not execute it. Yeah. And in fact, like there's like the entire results, they form into two fragments called the computational and the non-computational fragment. And so if you don't use axioms, it actually produces computer like machine code for your theorems. But if you do use axioms, it still type checks it, but it no longer. Oh yeah, okay, so close. Yeah. I mean, I write a computer code, and then the essential thing is to type check it. If it's in the computational fragment, it will actually generate machine code for you, and you could run it, but there's not actually a reason to do it. Yeah, I can. Yeah, it's a good question. Let me finish this, and then I'm probably, then I'm probably past my time, and then I can tell you some stories, and that's one story I can tell you. Okay, it gives rise to funny language. So here's like the internet chat server where all these people hang out and talk to each other. They don't say, "Oh, I've proved my theorem." They say, "This is this is a version I currently got to type check." Yeah. Does your code type check means I've proven my theorem in this community. All right, okay, so summary of the background part, which is probably all my time. So a theorem is an algorithm, I said that before, and to verify a theorem, you have to do type checking of its implementation. And so that's how these systems work. Okay, good, fine. Now I'm done with the introduction, and now I could stop, or I could tell you a few stories of what the system can do. They are all they don't connect, so they are all. Let me go very quickly through it for a few minutes, and then I'll leave you for a coffee break. So question one is, what can it do? And these systems are powerful enough now that they can formalize current research level math, some of it. For example, there was a big conjecture in additive combinatorics that has been around for a long time. It was recently solved by two field medalists, Gowers and Tao, and they immediately proceeded to formalize this thing in Lean. And now people are proving quantum information corollaries like in stabilizer testing based on these results. No? So current research level mathematics can sometimes be coded. They're good enough for this. What can't it do? Here's a website. It says missing undergraduate mathematics in Lean, and there's extremely elementary stuff like rank of a system of linear equations is currently not implemented. Yeah, so if you want to use it, you have to do it yourself. Like very easy stuff. So it's a bit uneven. Next question, also I got asked here, can it help me verify my results? Well, I don't know. So at the moment, I would say getting anything like getting the type checker to accept your proof is an order of magnitude harder than closing your office door, brewing coffee, and doing it by pen and paper, yeah, to like rigorous standards. That's if the underlying theory is already formalized. If not, you have a few months ahead of you of formalizing the ingredients. Let me tell you what happened to me. So I wanted to play around with it, so I wanted to set myself a goal. And I said, okay, why not? Let me formalize an infinite dimensional quantum Diffie-Netti theorem. But not actually quantum, because there was not enough operator algebra implemented at the time. Maybe it's different now, a year later. So let's use general probabilistic theories, which are more general than quantum, but also need less machinery to state. Yeah, and so, but I still need a notion of a local observable. So I need a notion of, in a tensor product, an observable that is non-zero on a finite subset and zero everywhere else. Yeah, the local algebra in algebraic quantum mechanics, you can say that for GPTs too. But this didn't exist. In fact, first we needed to talk about tensor products indexed by sets. So like something like this. You got a lattice system, and you got you take some subsites and you form the tensor product over the Hilbert spaces. That didn't exist in the library, so we started implementing this. So you can, so if you want to formalize something better, make sure the scaffolding is there. Okay. Computability. I have fun stories to tell about computability, but I skip them because I don't have time. They're still fighting about, pull or perish. That's also interesting, because now, if you have students, is it advisable to ask them to do stuff there, because they can't write papers so much, or you can, but maybe not. So let's see, how do you publish your results in this context? So the biggest game in town there is MathLab. So of course, if you now formalize something, you can put it on GitHub, or you can write a paper about it, but it will linger and get ignored. If you really want to help the community move forward, it should be part of this 2.5 million lines of library now, no? And so if you want to contribute, you have to make a pull request on their GitHub, all things I've learned after I turned 40, which might then well linger for weeks and months before it gets reviewed, because they are super overwhelmed now. There's a small number of maintainers with wide access to the repository who check for quality, and there's many people who want to contribute, so you will have to be patient. Then it gets reviewed line by line. It's a very arduous process, fit with the library, sufficient generality, style and maintainability. They want to have a library that can be maintained. Performance, also your question, I can show you in a second. Not for validity, obviously. No, because that's what the system does. They already know it's true what you do. Okay, acceptance bar is very high. I told you we wanted to get this contribute our work on tensor products indexed by set into the library. And we made a pull request here. Mr. Paradoxy is my student, and it was reviewed line by line. And at the very end, one of the maintainers said, so apologies for not raising it earlier, but this API, application programming interface, that's now applied to mathematics, makes me a little bit uneasy, because I don't think we have anything analogous anywhere. So why having tensor products indexed by sets and not first direct sums indexed by sets? He didn't know, and when in doubt, don't merge. Yeah, of course, we tried to convince him, saying, like in quantum information, we group tensor factors in very creative ways. No, that's a figure from like a Werner Schumacher paper on quantum cellular automata, where you have a lattice system and you divide it up into subsets into two incompatible ways and define, time evolution there. But this doesn't happen very often in the life of a pure mathematician. So at the moment, this pull request lingers on and is not yet merged, because there is no consensus that this concept is actually important. I think it will in the end come, but not for now. But also, if you have a student now, because the student worked on this for weeks, but it's not your project. It's not that you publish a paper and it's your decision what to include. It is their big engineering project to which you contribute, and they don't need a reason to say no. They just say, well, I will not maintain it. So for the student, it's a bit sad now, because, obviously. Idioms, can I use it? So for example, as a physicist, I want to say a vector space. No, a vector space is a normal mathematical object. How do you say vector space in Lean? That's the typical idiom. You declare a variable which is of a type and another variable k which is of a type, and you say that k is a commutative semi-ring, which is like the reals but much weaker, and E is an additive commutative monoid, which is like an additive group but much weaker, and there is a module structure between k and E. Yeah, so they try to be as general as possible. So you get a copy of this yellow book, no Bobaki, that All right, the bus test I will skip. Software engineering, because that was your question. So yeah, something that can now happen is that your proof is too slow. Not running it because they don't run it, but the type checking. So at some point, that was my pull request. There was like the Hahn-Banach theorem used a norm as an assumption where they could also use a semi-norm, which for some absurd reason I needed. So I weakened the assumption. And then on their GitHub, I called the benchmark robot. You talk to robot there, you say bench, and then some robot pulls your code and does a benchmark, and it says that it would take 130 trillion extra instructions to type check mathlib if the Hahn-Banach theorem works for semi-norms. Yeah, that's not acceptable. So I spent 1 weekend optimizing it. It's now, it says merged, so it's now part of the library, but only after I optimize it. So yeah, you spend a lot of your time not proving mathematics, but fighting with, the software engineering aspects of it. Okay, good. Misformalizations. I skipped that. It's a good story though, so ask me later. Should I learn it? Like, final thing. It's a very steep learning curve. I've been spending, my free time since more than a year on it, and I'm kind of now, I'm not an expert, but I kind of now maybe grok it a little bit. It's also still evolving, so everything you invest now will maybe become obsolete pretty soon. Pro, it's very satisfactory if things work out. They gamified math. You write a theorem, and when the type checker accepts your theorem, it puts like 2 check marks. Ding, ding. It's like my kids are addicted to Duolingo because they got streaks or something. Like, they hack your brain. And this is like me. It's like, ding, ding, your theorem type checks. Yeah. It might be part of our future. It's a good excuse to learn mathematical logic. So, but I think now you should learn it only if you're interested in the system. Yeah, as a tool, it's a bit too early. What will be the first use? That's going to be my last. So finding solutions for research level problems is still beyond the range of LLMs. They can't do it at the moment. But the following is now actually becoming slowly possible, namely an auto-formalization of papers. So if you have a paper that already has a result, and maybe you're a reviewer of a journal, you want to know, is it true before you go on to decide whether it's important. And this is no longer impossible, maybe. It's getting there slowly, that like not like ChatGPT normal subscription doesn't work, but if you have like a Claude super agent kind of setup, I don't have it, but I've seen other people do it. They can translate today's papers into bad lean code. It's not good enough to be in the library, but they find mistakes, or they can certify beyond the shadow of a doubt that the result is true. And I predict that the first thing that we will use them for is in a few years that journals will refuse to accept manuscripts if they are not accompanied with a proof of correctness generated by a large language model. That so that you at least know it's true. Okay, all right, that might be your future. Thank you.
Really, really good. Thank you for now. So questions? Do you want the microphone? No? Ask a question.
Yeah.
Thank you. No, again, a little bit more details about runtime. I would be interested. Like runtime linear. So you write this code that's never gonna run, and then you have another code that kind of gets as input this code, and it kind of decides where it type checks it, right?
Yeah, I mean, like the entire library, now it's 2.5 million lines of code. On my Office desktop, which isn't a very particularly powerful machine, it takes 40 minutes to type check the library.
The whole library.
Yeah. If you start from zero, after,
so
yeah.
The library is very optimized, let's say.
Yeah, they take a lot.
If you auto-generate, maybe this is gonna take.
Yeah, this is absolutely true. If you take LLM output, it will suck. It will not be readable. It will also be slow. And so they take a lot of care to have the runtime be reasonable. And you don't need to rebuild it. You can download like the binary distribution of the type check code from GitHub or whatever. But if you wanted to, and sometimes I wanted to, you can rebuild it on an Office computer in like less than an hour today.
Okay. Excellent.
Yep.
Just wanted to do some advertisement. I don't know if you heard, but there was a group of 3 people at the Perimeter Institute that made a lean repository for quantum information.
Yeah, Alex, my book. Yeah, they that's right. So I said, like, there's one game in town that's massive. That's another smaller game in town. Yeah, in fact, I have it open in VS. I can't with the computer. Yeah, I don't get it. Yeah, I have it open right here. I started looking at it only a few days ago, actually. And it's nice, but it's it's an individual effort mainly of one person. So in no way does it come close to MATLAB. And I think also like there's few like his bracket implementation. I read it on the airplane. Actually, I don't like it. So there's some quantum information being done there, obviously. So I wanted to do things that are more more using the infinite, where the system is really good at, like like infinite dimensions, infinitely many degrees of freedom. This I thought is not quantum info, but it's a better fit for the system first. But now recently I've also looked at it. It's interesting, but it's also not yet at the quality level that this MATLAB project has. Yeah. He's no longer at PI, by the way. He's now joined an artificial intelligence startup in California that he's at both still? Oh, right. Okay, Okay, good. Yeah.
Would it be possible to show an example of an axiom?
An example of an axiom?
Yeah.
Yeah, okay, sure. The biggest problem is that the two screen setup here that is beyond my abilities to handle. So the actual, like, okay, okay, maybe it works now. Right, okay. So here I have, let me make it bigger so you can see. Is it big enough? No. Okay, so here's how the system actually looks like. It's like this VS Code thing. So here's a a proof. That is this Hahn-Banach I mentioned. You can step through it line by line. This might actually be running. Oh no, it's local. Okay, now you want an axiom, but this is very easy. So let's say, okay, so let's make a theorem, and let's say we claim something wrong. So let's call it wrong, whatever, and we want to say 1 is 2. Yeah, and okay, it's one of type 1 and 2. And now it doesn't say it's wrong because it only checks proofs. It's not a proof, it's just a claim. So it says, okay, sure, 1 is 2, what about it? And now if I want to tell the system to accept it without me supplying a proof. What do you think I write? Yeah, I write sorry, which means I apologize to the system that I don't supply a proof, and it should just, the type checker should just accept it. So now there is, now I can write like a theorem, I don't know, like now I can write a theorem, true, no, a consequence, namely 1 is 2, and I can prove it by saying use wrong. And then it accepts it. So this is the double check mark. It says, yeah, you've proved it. But of course, I proved it. You're writing on an axiom, on a sorry statement. Yeah. And the actual MATLAB uses basically no axioms. It uses a version of the axiom of choice, and it derives the law of excluded middle from it, and it uses an axiom that says that the action of taking quotients, like a quotienting out by an equivalence relation, is well defined. That's it. Yeah. So these two you can use. You can't use any others. Mm-hmm.
Very smart, this double check, because it's a kind of dopamine to users to continue working.
Yeah,
yes?
yeah. It's totally, it's hacked my brain chemistry, that thing. Yeah. Come to bed. No, my proof doesn't type check. Yeah. Yeah. Mm-hmm.
Okay, so let's thank David again.